Here we're going to look at a classic type of an arithmetic puzzle. So we want to determine which one of these numbers is larger, 50 to the 99 or 99 factorial. We're going to do this three different ways. One way, which is like a pretty simple calculation. Another way where we prove a general statement that will imply this. And then another way, which I'm going to call cheating. We'll see what that is at the end. Okay, so let's maybe get to the simple calculation first. So I'm going to look at the quotient 50 to the 99 divided by 99 factorial. And if I can reduce this to something which is clearly larger than 1, then I know that the numerator is larger. But if I reduce that to something that is clearly smaller than 1, then that means that the denominator is larger. So let's see which one we get. So I'm going to expand this numerator a little bit. So I'm obviously not going to write all of the 50s, but I'm going to write enough so that we can see the structure of our argument. So let's write this as 50 all the way down to 50. And then I'm going to have this 50, which is in the middle, and then 50 all the way and another 50. So that's what it's going to be, the numerator. Okay, and then I want to talk about how many 50s do I have there. So I'm cutting this right in half. So since 99 is an odd number, I know that it has a middle point. And if I cut it right in the middle, then that's going to cut it at the, well, let's see, it's the 49th number. So that means there are 49 50s right here. And there are also 49 50s right here. Okay, cool. Leaving 150 in the middle. Notice 49 plus 49 is 98, plus 1 is 50. Now we're going to do the same thing with 99 factorial. So we're going to write that as 99 times 98 all the way down. I'm going to have 51 times 50 times 49 all the way down to 2 times 1. Okay, now I'm going to group these in a careful way so that I have parts which are clearly smaller than 1. The way that I'm going to do that is like this. So I'll group this 50 times this 50 divided by this 51 times this 49. You can check that that is smaller than 1. And then I'm going to group the next 50 with the 50 right before this, along with the 52 and the 48, and then so on and so forth. All the way down until I'm grouping this 50, this 99, with this 50, and then this number 1. So I want to point out that using that strategy, I've used everything in the denominator so far except for this middle term. And that's really good news because we can group this middle term with the middle term in the numerator, and those divide out to be equal to 1. Okay, so now let's write what we've got. So we've got 50 squared over 99 times 1. So that's what's underlined in yellow. And then next, we're going to have 50 squared times 98 divided by 2, all the way down to 50 squared divided by 51 times 49, and then finally 50 divided by 50. So we've just reordered that product. But now it's pretty easy to check that 50 squared divided by 99, that's going to be bigger than 1. Well, 50 squared is like 2,500, but 99 is clearly smaller than that. And then all the way up to this thing right here. So I want to point out that these denominators are increasing, but they're only increasing to 2,499. That's what that product is there. And so that makes this numerator, which is 2,500, always bigger. So here, this is going to be bigger than 1 times 1 times 1, a bunch of 1s, times 50 over 50, which is equal to 1. So we've got 50 to the 99 over 9 factorial is bigger than 1, which tells us that 50 to the 99 is bigger than 99 factorial. And we've done our first method. Okay, we just finished our simple calculation proof that 50 to the 99 was bigger than 99 factorial. Now we're going to prove a general statement which will imply this statement. And we're going to prove that for all natural numbers bigger than or equal to 2, we have n plus 1 over 2 to the nth power is bigger than n factorial. Now notice that what we just showed is the 99th case of this. So this is indeed a general case of our specific statement which we just calculated. So we're going to prove this by induction, meaning that the first step is to prove a base case. And since we're starting at n equals 2, our base case will be the n equals 2 case. So let's notice that if we plug n equals 2 into this, we're going to get 3 over 2 to the 2, but that's going to be equal to 9 over 4. But 9 over 4 is most definitely bigger than 2, which is equal to 2 factorial. That's because 9 is bigger than 8, and 8 over 4 is equal to 2. So definitely our base case holds. So next we're going to make an induction hypothesis. So in other words, we want to suppose that this statement is true for some k bigger than or equal to 2. So let's suppose for k bigger than or equal to 2, we have the following statement. So we have k plus 1 over 2 to the k is bigger than k factorial. So again, that's our induction hypothesis. And then next what we want to do is consider the k plus first case. So we'll start at the left-hand side of this inequality and then decompose it a little bit until we can use the induction hypothesis. Okay, so let's get to that. So I'm going to write the k plus 1 version of this inequality in the following way. So we've got k plus 2 over 2 to the k plus 1. So that's clearly what we get if we replace k with k plus 1 in the left-hand side of this inequality. But I'm going to rewrite this a little bit. I'm going to rewrite this as k plus 1 over 2 to the k plus 1. So it's pretty clear that we can do that. And then next, I'm going to apply binomial expansion to the numerator here. Well, and then just we're exponentiating the denominator. So let's maybe go ahead and do that and see what we get. So applying binomial expansion to the numerator will give us k plus 1 to the k plus 1 plus k plus 1 choose 1 times k plus 1 to the k, or k plus 1 minus 1. So let's maybe write that down. That gives us k plus 1 times k plus 1 to the k plus, and now here I'll just put lower order terms. So that's what happens in the numerator. So maybe I want to point out here that the coefficient here of 1 we're getting by taking k plus 1 choose 0. The coefficient we're getting here as k plus 1, that's going to be the binomial coefficient k plus 1 choose 1. And then working down, the next coefficient will be the binomial coefficient k plus 1 choose 2, and then so on and so forth down the line. Okay, great. And then next, I want to notice that in the denominator, we're just going to simply have 2 times 2 to the k. So I'll write it like that, although that's clearly 2 to the k plus 1. Okay, next I want to introduce an inequality. So I'm going to use the fact that all of these lower order terms are bigger than 0 to just get rid of them and realize that we're going to get something smaller. So let's see what we do when we do that. So this is going to be bigger than k plus 1 to the k plus 1 plus, then I'm going to combine those two into another k plus 1 to the k plus 1 over 2 times 2 to the k. So like that. Okay, next what I want to do is maybe notice I've got 2 times k plus 1 to the k plus 1 in the numerator. I can add those together and then cancel out the coefficient with this 2 in the denominator. But now that puts me very, very close to my induction hypothesis. So I can factor a k plus 1 out of this, and that'll leave me with k plus 1 to the k over 2 to the k. But look, this term right here is exactly what I have in my induction hypothesis. So that means I can replace that with k factorial if I put it the correct inequality. So this is going to be bigger than k plus 1 times k factorial, but k plus 1 times k factorial is k plus 1 factorial. And thus, we've established this claim by induction, and the 99th case of this claim is our goal statement. So we're done with our general way. Now we're going to prove this by cheating a little bit, but we can't do that with the chalkboard, so we're going to need another tool.